Bismillahirrahmanirrahim. In this video, we will discuss the components of the voltage drop in a DC shunt generator. One voltage drop is because of the armature resistance, and the other one is because of the armature action that we have discussed in the theory class. So, this one is the terminal board, this one is the load unit. You can see the meters as well on this setup. So, we will be connecting this load, and this is our power supply unit providing power to our terminal board that will be converted into DC and then will be used to power up our DC machines. So it's a variable transformer in the AC machine giving supply to this terminal board. So we will be connecting these meters as per our requirement. One is configured as a DC milliampere. The second one is the voltmeter configured or scaled at 200 volt, and this one is the ammeter with the 20 ampere scale, and this one is the tachometer. And on the back side you can see the two machines which are coupled, field winding, armature winding, and you can see the nameplate of your machine, the rated values of this machine. This may be used as a motor or as a generator. We will use one of the machine as the motor and the second machine as the generator. So construction wise both are same, but in this case the DC motor will act as a prime mover for the generator. We'll be rotating that one, and then we will be connecting the load at the terminals of the shunt generator. Now let's start the wiring. We start joining these components. So you can observe the supplies. So first of all we are going to take the supply from the 300 volt supply, which can give 6 ampere at the maximum, and we will power up our armature. We are configuring it as a DC motor. So we will give it a supply. We will give supply to the armature from this power supply. So we have given it to the armature of this machine, and now we will connect the field in parallel to the armature. So we can connect A to F2, A1 F1, or A2 with F1 and A1 with F2. In all cases the field winding will be in parallel with the armature. So here you can see the connections. So we have configured our machine as a DC shunt machine. Okay, so this is our first step. So how you can reverse the direction of the motor? By swapping the two terminals of the field or of the armature, because we need to reverse the current in one of the winding, then the direction of rotation of the machine is reversed. That we have discussed in our theory class. Okay, now this machine will be configured as a generator. So we are going to first of all connect the armature with the meter, and that meter is configured as the ammeter. Okay, so ammeter is in series, and then we are going to connect a rheostat in series because we want to change the current with the help of this rheostat. And basically you can observe that this field winding F1 and F2, that is in series with the ammeter, and that is in series with the rheostat, and then we are going to connect this series combination of rheostat, ammeter and field winding in parallel to the armature. You can draw a circuit diagram on a page, and then you can better understand that how we have connected. Just observe the connections over here. Right now we will take this output from the armature. We will connect our load in parallel to the armature. At this point what we have ammeter, rheostat is in series with the field winding, and that is connected across the armature. And here you can observe we are taking this wire from the armature, right, and we are going to connect a voltmeter in parallel to the armature. So this meter is configured as a voltmeter. One terminal from one A1 and the other is the A2. From these two we have taken two wires, and we are going to connect in parallel to the armature. So this will be measuring the voltage across the armature terminals, and that you can see over here. Now that these two terminals are in parallel with field winding, which is in series with ammeter and the rheostat. Okay, so this is voltmeter. For voltmeter, you use these two terminals and you must select the proper scale. Okay, now you can see the setup and the connections of the meters. What we are going to do, we are going to connect load across the armature terminals. So there is an ammeter to measure the load current, and you know that we have connected the armature with the voltmeter. So voltmeter terminals are just like your armature terminals. So we have connected an ammeter in series, and now we are giving the path through the load, and then this load will be connected at the armature terminals. Center meter is the voltmeter. It is connected in parallel to the armature. That's why we have connected the wires over here. You can connect these wires at the armature terminals. So this completes the wiring for this particular setup. What we have done, we have connected a voltmeter in parallel to the armature of the DC shunt generator. We have connected an ammeter in series with the field winding, and we have connected an ammeter in series with the load. So first of all, we have disconnected the load, and we are going to run our DC motor at a particular speed. When we are going to observe the meters, are those working properly, and then we will start our experiment. Okay, so first of all, observe the readings. When you are increasing the power supply, the voltage is increasing, the speed is increasing, right? And the field current is increasing because these meters are connected on the generator side, and this is the tachometer, which is measuring the speed of the machine, right? So how to increase the motor speed? Increase the voltage that is applied to the motor terminal. We are not measuring those ones because in this experiment we are just supposed to measure the parameters at the generator terminal, because we want to find out the voltage drop components in the shunt generator. One voltage drop is because of the armature resistance, and the second voltage drop is because of the armature reaction. The meter was showing the negative value. We have just swapped the terminals so that it shows the positive values. No change in the connection. We have just swapped the terminals such that it gives us the positive reading, because the direction of the current will be changed in the meter if you swap the terminals. Okay, so now you can observe the armature voltage and the field current, but now we are going to connect the load. As we have connected the load, you can observe there is the load current now. It's negative. Again, to make it positive, you can swap the terminals at the meter, and the load current will be shown as positive. That you can see, we are going to do it over here. Okay. And how to change the load? There is a slider on one side of the load. You will be sliding that one. The load resistance will be changing, and the load current will change. So you can observe the slider. Okay, again we have disconnected the load, and we are going to adjust the field current at one particular value. And what is that? This is set to this one. Okay. Okay, so now you can observe the values, right? And now we are going to connect the load back, and now you can see the load current is there. There is the voltage drop because of the armature resistance. The terminal voltage has reduced. Okay, the field current is also reduced because once the armature voltage is reduced, it is providing power to the field winding. Field voltage is reduced, field current is reduced, so there is the reduction in the magnetic field in the generator, and because of that there is the voltage reduction across the terminals. So what is the procedure in this experiment? First of all, you will vary the load, and you will run the machine at one constant speed. You will vary the load and you will observe the change in the voltage across the armature terminal. And of course, your shunt generator has the field winding parallel to the armature, and if you do not change the field resistance, the current will change because of the change of the armature voltage, and that is appearing across the field. So the field current will change when the armature voltage will change. So when you will be changing the load from 0 to the maximum level, the terminal voltage will drop, and because of that the field current will also drop, and the magnetic field in the machine will be reduced, and there will be a voltage drop because of that. So in the first part of the experiment, you will be increasing the load, you will be maintaining the speed, but you will not set the current back to the original value, particularly in the field winding, because that will be dropped because of the change of the field voltage. And you will record the voltages at different values of the load. Then in the second part of the experiment, what you will do, you will set up the same loads, but now this time what you are going to do, you are going to maintain the field current back to its original value, what it was, with the help of the rheostat that you will be connected, that you have connected in series with the field winding. And once your field current is adjusted back, then the voltage drop is only because of the armature resistance, not because of the weakening of the flux. So in this way you can separate out the armature reaction voltage component and the voltage drop because of the armature resistance. Okay, so I am repeating. First of all, you will increase the load, you will not set the field current at the constant level, rather you will maintain this constant speed only, and at different values of the load, let's suppose 1 ampere, 2 ampere, 1.5 ampere, 2.5 ampere, 0.5 ampere, select 5 or 6 readings and observe the voltage drop without adjusting the field current. Then at the same value of the load, repeat the experiment at the same values of the load, same speed, but now this time adjust the field current back to the original value, because when you will increasing the load, field current will decrease because of the decrease in the terminal voltage. Set it back to the original value, such that you only have the voltage drop because of the armature resistance. So the difference of the two values, one with the constant IF and one without the constant IF, when you have allowed the field current to change, that is going to give you the voltage drop because of the armature resistance. Okay, and so you can separate out the voltage drop because of armature reaction and armature resistance. We have discussed the armature reaction in the theory class, that the current in the armature winding distorts your main field and cause the weakening of the main field, and because of that in the generator there is the reduction in the induced EMF, and in the case of motor there is the increase of the speed, because you know that the speed is inversely proportional to the flux. The first effect of the armature reaction in the generator is the reduction in the induced EMF, and in the motor is the change in the speed that increases because of the weakening of the flux. And second impact of the armature action is the shifting of the magnetic neutral axis that may cause the arcing and sparking at the carbon brushes, and that we have discussed in detail in the theory class. Okay, now you can follow along this video till the end. You will see that we have taken the readings at the different voltage at different load levels, and all of those values are shown over here. You can observe the field current, you can observe the load voltage, you can observe the load current, you can observe the speed. All that is required to plot the voltage drop at constant speed and without at constant speed and varying field current, and then at constant speed and fixed field current. So go through the video till the end. You can observe the readings, then follow your lab manual and draw the graphs, and then separate out the voltage drop because of the armature resistance and the armature reaction. Right? This is the objective of this one, that you should be able to separate out how much voltage drop is because of the armature resistance and how much voltage drop is because of the armature action. Armature action causes the flux weakening, distortion of the magnetic neutral axis. So now you can see the videos. I was discussing, but the experiment was going on. You can observe the readings and you can study the concept that I have explained to you. So that's all from my side. Follow the video till the end, note down the readings in your manual and answer the short questions given in the manual and calculate all the voltage drop components. Thank you very much.